Hello, friends. Welcome back to another journey through the cosmos, where we explore the wonders of the universe in that gentle, contemplative way that helps us both learn and unwind. Tonight, we're going to discover something truly extraordinary, something so vast that it challenges everything we thought we knew about the scale of cosmic structures. Picture this. It's a cold February night in 2022 at the Leiden Observatory in the Netherlands. A team of astronomers is doing what astronomers do, best staring at data, lots and lots of data. But on this particular night, something catches their eye. Hidden in the radio observations from the LOFAR telescope network, they spot a structure. And as they trace its edges following the faint radio emissions across the sky, they realize they're looking at something that shouldn't exist. Something impossibly magnificently huge. A galaxy spanning not millions, not tens of millions, but 16 million light years from end to end. They have just discovered Alcyoneus, the largest galaxy ever found in the universe. If you're enjoying this cosmic journey and want to explore more wonders of the universe with us, take a moment to hit that like button and subscribe. It truly helps us continue bringing you these stories from the edge of human knowledge told in a way that invites both curiosity and calm. And don't forget to turn on notifications so you never miss our explorations of the cosmos. Now, let's talk about what 16 million light years actually means, because our minds aren't really built to comprehend distances like that. The Milky Way. Our home galaxy stretches about 100,000 light years across. That's already incomprehensibly large. Light traveling at 186,000 miles per second takes 100,000 years to cross from one side of our galaxy to the other. But Alcyoneus. If you place the Milky Way inside Alcyoneus, it would be like placing a single coin on a football field. Actually, that comparison doesn't do it justice. It would be more like placing a grain of sand on that football field. Alcyoneus is 160 times wider than our entire galaxy. Let me give you another way to think about it. If you could somehow travel at the speed of light, the fastest speed possible in our universe, it would take you 16 million years to cross from one end of Alcyoneus to the other. When the light we're seeing now left one side of this galaxy, our ancient human ancestors hadn't even evolved yet. Dinosaurs hadn't evolved yet. Complex life on Earth was just beginning to take hold in the oceans. The Discovery team chose the name Alcyoneus from Greek mythology, and it's a fitting choice. In ancient Greek legends, Alcyoneus was the king of the Gigantes, the giants born from Gaia, the Earth itself. He was said to be immortal as long as he remained in his homeland of Palin. The hero Heracles ultimately defeated him, but only by dragging him beyond the borders of his territory. For a galaxy of such staggering proportions, the name of the King of Giants seemed appropriate. And like its mythological namesake, this cosmic giant rules over its own vast territory in space. But here's where things get interesting and perhaps a bit confusing. Before Alcyoneus claimed the title, another galaxy held the record for decades. You might have heard of it, IC1101. And depending on how you measure, IIC1101 is still the largest in certain ways. You see, measuring galaxies is not as straightforward as you might think. It's not like measuring a building where you can just stretch a tape measure from one end to the other. When we talk about a galaxy's size, we could mean several different things. We could measure the stellar extent, how far the actual stars of the galaxy spread out into space. By this measure, IC1101 still wins with stars scattered across about 6 million light years. Or we could measure the total structure, including the enormous plumes of energetic particles and radio emissions that some galaxies produce. By this measure, Alcyoneus is the undisputed champion. Think of it like comparing two cities. One city might have buildings spread across a larger area, while another city might have highways and infrastructure extending much farther out. Which city is bigger? It depends on what you're measuring. IC110. One has more stars spread over a larger volume of space. But Alcyoneus has these spectacular jets of plasma shooting out from its center, creating enormous radio-emitting lobes that extend 8 million light-years in each direction. What exactly are these radio lobes? Imagine the galaxy's central supermassive black hole as a cosmic fire hose, shooting jets of superheated plasma out into space at nearly the speed of light. Those jets travel for millions of years, carving channels through the thin gas between galaxies until they finally slow down and spread out into vast bubbles, the lobes. These lobes glow with radio waves, invisible to our eyes but bright as beacons to radio telescopes. And in Alcyoneus, these lobes have grown to unprecedented size. The discovery of Alcyoneus wasn't made by a lucky accident. It was the result of a technological revolution in astronomy. The LOFAR telescope network, which detected these massive radio structures, isn't a single telescope at all. It's a collection of about 20,000 individual radio antennas spread across Europe, all working together as one giant eye on the radio sky. This network can detect faint radio emissions that previous generations of telescopes would have missed entirely. The astronomers led by Martin Oé and his colleagues were analyzing the second data release from LOFAR's survey of the northern sky when they spotted the telltale signs of this cosmic giant. What struck the research team wasn't just the size, it was the ordinariness of the galaxy at the center. You'd expect that to create such an enormous structure, you'd need an extraordinary galaxy with an exceptionally massive black hole, right? But Alcyoneus defied expectations. The host galaxy is relatively normal. Its central black hole weighs in at about 400 million times the mass of our Sun. That's certainly massive, but it's actually on the smaller side compared to most giant radio galaxies. The galaxy itself contains about 240 billion times the Sun's mass, roughly half the mass of the Milky Way. This ordinariness is what makes Alcyoneus so puzzling. If an average galaxy with an average black hole can create the largest structure ever found, what does that tell us about galaxy evolution? What special circumstances allowed this particular galaxy to grow such enormous lobes? These questions open new chapters in our understanding of how galaxies grow and evolve over cosmic time. Consider the journey that brought us to this moment of discovery. For most of human history, we didn't even know galaxies existed beyond our own. The fuzzy patches of light that telescopes revealed in the night sky were called nebulae, and many astronomers believed they were simply clouds of gas within the Milky Way. It wasn't until the 1920s, when Edwin Hubble measured the distance to the Andromeda galaxy, that we realized our galaxy was just one of billions scattered throughout space. From there, the race was on to catalog and measure these island universes. William Herschel, the astronomer who discovered Uranus, also cataloged thousands of nebulae in the late 1700s, including what we now know as IC1101, though he had no idea of its true nature or distance. As telescopes grew more powerful through the 20th century, we began to realize just how large some galaxies could be. Giant elliptical galaxies sitting at the centers of galaxy clusters seemed to dwarf everything around them. But those were all measurements of starlight, the visible glow of billions of suns. The radio universe remained hidden until the mid-20th century, when astronomers developed new technologies to detect radio waves from space. Suddenly, we could see structures invisible to optical telescopes. Some galaxies we discovered were surrounded by vast halos of radio emission. A few had dramatic jets shooting out from their centers, and an even smaller number had enormous double lobes, one on each side, like cosmic dumbbells. These giant radio galaxies became objects of intense study. How did they form? What powered their jets? How large could they grow? Each new discovery pushed the boundaries of what we thought possible. And then came Alcyoneus, pushing those boundaries farther than ever before. Have you ever stood beneath a clear night sky far from city lights and tried to comprehend the distances involved? The stars you see are mostly within a few hundred light years of Earth neighbors in cosmic terms, all part of our local stellar neighborhood within the Milky Way. The galaxy itself extends 50,000 light years above and below the disk we inhabit. And beyond our galaxy like countless others scattered across billions of light years of space. Alcyoneus, at 16 million light years across, spans a distance greater than most galaxy clusters' entire collections of hundreds of galaxies. The discovery reminds us that the universe still holds surprises. Despite decades of increasingly sophisticated surveys and telescopes that can peer back to the dawn of time, we're still finding things that don't quite fit our theories. Alcyoneus shouldn't exist according to our simple models of galaxy growth. The fact that it does suggests we're missing something important in our understanding. What's particularly beautiful about this discovery is how it challenges our intuitive sense of biggest. In everyday life, the biggest things are usually the most massive, the most powerful, the most dramatic. But Alcyoneus achieved its record size with remarkably ordinary equipment, cosmically speaking. It's like discovering that the tallest building in the world was built in a small town with a modest budget and a regular construction crew. The achievement isn't diminished, if anything, it becomes more intriguing. How did they do it? As we continue our journey through this story, we're going to unpack that question from every angle. We'll explore the physics of how supermassive black holes create these enormous structures. We'll visit IC1101, the previous record holder, and understand what makes it extraordinary in its own right. We'll dive into the role that environment plays in allowing galaxies to grow to such staggering proportions. And we'll consider what these cosmic giants tell us about the evolution of the universe itself. But right now, I want you to just sit with the wonder of it. Somewhere out there, 3 billion light years away, meaning we're seeing it as it was, 3 billion years ago, when Earth was still a planet covered in simple microbial life. This enormous galaxy spans a length that light itself needs 16 million years to cross. Its jets have been firing its lobes expanding for hundreds of millions of years. It existed before our solar system formed. It will likely exist long after our sun has died. The cosmos operates on scales that dwarf our everyday experience so completely that they can seem almost abstract. But they're real. Right now, at this very moment, photons that left Alcyoneus 3 billion years ago are striking radio antennas across Europe, carrying with them information about this cosmic giant. Those radio waves traveled through the expanding space of the universe across distances our ancestors couldn't have imagined, to arrive at precisely this moment in time when we have the technology to detect them and the curiosity to wonder what they mean. This is the magic of astronomy. It allows us to transcend the limitations of our brief lives and small bodies, to reach out across space and time and touch something vast and ancient and magnificent. Every discovery, like Alcyoneus, reminds us that we're part of something much larger than ourselves, something that extends across billions of light years and billions of years. Now that we've met this cosmic giant and begun to grasp its incredible scale, the natural question arises: how do galaxies actually grow to such enormous sizes? What cosmic processes build these titans of space? To understand Alcyoneus and what makes it so special, we need to understand the architecture of galaxy giants in general, the fundamental principles that govern how these massive structures form and evolve over billions of years. Galaxies don't spring into existence fully formed. They grow, they evolve, they collide and merge and transform over billions of years. And the story of how they reach titanic proportions, like Alcyoneus or IC1101, is one of cosmic violence, patient accumulation, and the invisible hand of dark matter sculpting structures across the universe. Imagine you're watching a time lapse of galaxy evolution, but instead of hours compressed into seconds, you're watching billions of years compressed into minutes. In the early universe, just a few 100 million years after the Big Bang, the first galaxies were tiny things, scrappy collections of hot young stars, each galaxy containing maybe a few million stellar masses. Nothing like the giants we see today. But then something remarkable happens. These small galaxies start finding each other drawn together by gravity's patient pull. They collide, they merge, they grow. And over billions of years, through countless collisions and mergers, some of them become monsters. If you're finding this journey through cosmic evolution as fascinating as I am, and you'd like to explore more of these deep questions about our universe, please take a moment to like this video and subscribe to the channel. Your support helps us continue creating these in-depth explorations of the cosmos, and it means more than you might think. This process of galaxy growth through mergers is sometimes called galactic cannibalism, and it's not a gentle process. When two galaxies collide, and yes, galaxies do collide, despite the vast emptiness of space, their stars rarely actually hit each other. The distances between stars are so enormous that two colliding galaxies can pass right through each other, like two clouds of gnats interpenetrating. But gravity doesn't pass through. Gravity links and binds and tears. The gravitational forces during a galaxy merger can fling stars into new orbits, trigger massive bursts of star formation as gas clouds collide and compress, and send streams of stars spiraling out into space in long tidal tails. We see evidence of these cosmic collisions everywhere we look. The antennae galaxies about 45 million light-years away are caught in the act right now. Two spiral galaxies in the process of merging with long streamers of stars, arcing out into space like the antennae of an insect. The collision has triggered an explosion of star formation, lighting up the merger zone with brilliant blue clusters of newborn stars. In a few billion years, these two galaxies will settle down into a single elliptical galaxy, their spiral structures erased by the violence of the merger. And here's something crucial to understand. The largest galaxies in the universe are almost always elliptical galaxies, not spirals like our Milky Way. Why? Because elliptical galaxies are in many cases the products of major mergers. When spiral galaxies collide, their delicate disk structures get scrambled. The ordered rotation of stars around the galactic center gets disrupted. What emerges from the collision is a more chaotic system, a swarm of stars orbiting in all different directions, creating that smooth elliptical appearance. Both IC 1101 and the host, galaxy of Alcyoneus, are elliptical galaxies. They achieved their size through multiple merger events over billions of years, consuming smaller galaxies and growing ever larger. But here's where the story gets even more interesting. The visible matter, the stars and gas that we can see, represents only a small fraction of a galaxy's total mass. The vast majority of the mass in any galaxy is dark matter, that mysterious substance that doesn't emit light but makes its presence known through gravitational effects. Dark matter forms a kind of invisible scaffolding throughout the universe, and it's this scaffolding that determines where galaxies can form and how large they can grow. Think of dark matter as the foundation and frame of a building. The visible galaxy, the stars and gas is like the walls and windows and furniture. You can't see the foundation and frame, but without them, the building couldn't exist. Dark matter halos extend far beyond the visible edges of galaxies. And when galaxies merge their dark matter, halos merge too, creating even larger gravitational wells that can attract and hold more matter. The largest galaxies in the universe typically reside at the centers of galaxy clusters, collections of hundreds or even thousands of galaxies bound together by gravity in a region spanning several million light-years. IC 1101, for instance, sits at the heart of the Abel 2029 cluster. These central cluster galaxies, as they're called, are like cosmic vacuum cleaners. Their position at the bottom of the cluster's gravitational well means that matter naturally flows toward them. Smaller galaxies that wander too close get torn apart by tidal forces, their stars added to the growing giant. There's a specific term for the largest, brightest galaxies at cluster centers, brightest cluster galaxies, or BCGs. These objects are among the most massive single structures in the universe. They're typically supergiant elliptical galaxies with masses ranging from hundreds of billions to over 1 trillion times the mass of the Sun. They often have extensive halos of stars that don't orbit in any organized pattern, These are the remains of smaller galaxies that have been shredded and absorbed. The formation of BCGs is an ongoing process. Even today, we can observe galaxies falling into clusters and being slowly torn apart, their stars scattered into the diffuse halo around the central giant. It's a slow-motion cosmic demolition taking hundreds of millions of years to complete. Some astronomers estimate that a galaxy like IC 1101 has consumed hundreds of smaller galaxies over its lifetime, growing incrementally with each merger. Now, let's think about the role of time in all this. The universe is 13.8 billion years old. That might seem like an eternity, but it's actually a crucial constraint on how large structures can grow. Galaxies form and merge over hundreds of millions or billions of years. There simply hasn't been enough time in the history of the universe for infinite growth. Additionally, the expansion of the universe itself works against the formation of larger structures. As space expands, carrying distant galaxies farther apart, the opportunity for mergers decreases. Dark energy, that mysterious force driving the accelerated expansion of the universe, puts an ultimate limit on how large gravitationally bound structures can become. Galaxy clusters that are forming now will continue to grow for a while, but eventually the expansion of space will overwhelm gravity's pull, and isolated clusters will find themselves increasingly alone in an expanding void. In the far future, trillions of years from now, individual galaxy clusters will be like isolated islands unable to interact with others because the space between them is expanding faster than light can travel across it. This means we're living in a special era, a cosmic sweet spot, where the universe is old enough to have built impressively large structures, but not so old that expansion has completely isolated everything. Alcyoneus and C110 are likely close to the maximum size that single galaxies can achieve, given the age and expansion rate of our universe. Let's talk about a common misconception. Many people imagine that larger galaxies must be younger, still actively growing, but actually the reverse is often true. The largest galaxies are typically old, their star formation largely finished. They're sometimes called red and dead galaxies because they shine with the reddish light of old stars and have very little ongoing star formation. They've used up or lost most of their gas, the raw material, for making new stars. IC1101 is a perfect example. Despite its enormous size, it's a dying galaxy, having converted most of its gas into stars long ago. Why do giant galaxies stop forming stars? Part of the answer involves their central supermassive black holes. As matter falls into these black holes, it doesn't just disappear quietly. The accretion process matter, spiraling inward, generates enormous amounts of energy. This energy can heat up the remaining gas in the galaxy to such high temperatures that it can no longer collapse to form new stars. The black hole, in effect, regulates the galaxy's growth by shutting down star formation. It's a negative feedback loop that prevents galaxies from growing indefinitely. The history of our understanding of galaxy formation and evolution is itself a fascinating story. In the early 20th century, when Edwin Hubble first proved that spiral nebulae were actually distant galaxies, astronomers initially thought that galaxies came in a few basic types, and that was that. Hubble created a classification scheme, the famous tuning fork diagram, that sorted galaxies into categories, ellipticals, spirals, and irregulars. For decades, this simple picture dominated astronomy, but as telescopes improved and observations accumulated, the picture grew more complex. We realized that galaxies aren't static objects, but evolving systems. We discovered that most galaxies harbor supermassive black holes at their centers. We found evidence of past mergers in the form of tidal streams and shells of stars. We detected the invisible dark matter halos. We observed galaxies in the process of colliding and transforming. The simple classification scheme gave way to a rich understanding of galaxy evolution as a dynamic, ongoing process. The Hubble Space Telescope, launched in 1990, revolutionized our understanding by providing deep images of distant galaxies as they appeared billions of years ago. By looking at galaxies at different distances, and therefore different times in cosmic history, we could piece together the story of how galaxies evolve. We saw that galaxies in the early universe were smaller, more irregular, more actively forming stars. We watched the merger rate decline over time as the universe expanded. We observed how galaxy clusters assembled themselves over billions of years. Consider the Milky Way our home galaxy. It's not a giant by any means, what we call a medium-sized spiral galaxy with a mass of perhaps 400 billion suns. But the Milky Way is still growing. It's currently in the process of consuming several smaller satellite galaxies, including the Sagittarius dwarf elliptical galaxy, which is being slowly torn apart by tidal forces. Streams of stars from this disrupted galaxy now wrap around the Milky Way like ribbons. In about 4 billion years, we're due for a major merger with the Andromeda Galaxy, our large spiral neighbor. The collision will scramble both galaxies, likely producing an elliptical galaxy that future astronomers might classify as a BCG, if our local group of galaxies eventually grows into a larger cluster. This brings us back to Alcyoneus and IC 1101. Both are products of billions of years of growth through mergers and accretion. Both reside in environments where matter naturally flows toward them. Both have supermassive black holes at their centers that have shaped their evolution. But there's something about Alcyoneus that sets it apart, not the size of its galaxy proper, but those enormous radio lobes extending millions of light years into space. To understand how those lobes form and why Alcyoneus's lobes grew so extraordinarily large, we need to understand the specific mechanisms that create giant radio galaxies. It's not enough to have a massive elliptical galaxy. You need a supermassive black hole that's actively feeding and producing jets. You need those jets to plow through the surrounding medium for hundreds of millions of years. And perhaps most crucially, you need the right environment, one that allows those jets to expand to unprecedented sizes. But before we dive into the physics of how Alcyoneus created its record-breaking lobes, we should meet the previous champion up close and personal, IDC 110. One held the title of largest known galaxy for decades, and it's still the largest in terms of stellar extent. Its story is different from Alcyoneus, but equally remarkable, a tale of gravity mergers and a black hole so massive that it defies the upper limits of what we thought possible. On a June evening in 1790, William Herschel pointed his telescope toward a region of sky between the constellations Virgo and Serpens. Herschel was already famous by this point. 9 years earlier, he discovered Uranus, the first planet found in recorded history that wasn't known to ancient astronomers. But on this particular night, he was engaged in his life's great project, systematically cataloging every fuzzy patch of light in the night sky. He noted a dim nebulous object and recorded its position. He had no idea he'd just observed the largest elliptical galaxy in the known universe, a cosmic leviathan containing 100 trillion stars. That object, eventually cataloged as IC101 in the Index Catalog of Nebulae and Star Clusters in the late 1800s, would hold the title of largest known galaxy for over 2 centuries. Even after Alcyoneus claimed the overall size, record IC110, 1 remains the largest galaxy by stellar extent, the actual spread of its stars. To understand what makes IC110, 1 so extraordinary, and why it held the record for so long, we need to journey back to that distant cosmic empire and explore its golden realm. If this deep dive into the cosmos resonates with you, I'd be grateful if you'd take a moment to like this video and subscribe. These stories take considerable research and care to craft, and your support helps us continue exploring the wonders of the universe together. IC1101 sits at the gravitational heart of the Abell 2029 galaxy cluster, located about 1.15 billion light-years from Earth. That's an almost incomprehensible distance. The light we see from IOC1101 today left that galaxy during the Proterozoic eon on Earth, a time when our planet was inhabited only by single-celled organisms, and the first simple multicellular life was just beginning to emerge. No fish, no plants, no animals of any kind. Just microbial mats and primitive algae in ancient oceans. The light from IC1101 has been traveling through space for longer than complex life has existed on Earth. Let's talk numbers, because with IC1101, the numbers are staggering. The galaxy spans approximately 5.5 to 6 million light-years in diameter when you measure its stellar extent. To put that in perspective, if IC1101 replaced the Milky Way, at the center of our local group of galaxies, its outer edge would extend most of the way to the Andromeda galaxy. Think about that. Andromeda is our nearest large galactic neighbor about 5 million light-years away, and we consider it a separate distant galaxy. IC1101 stars would fill almost that entire space. The galaxy contains an estimated 100 trillion stars. Let me write that out, 100 quadrillion stars. Our Milky Way, which we consider a large galaxy, contains somewhere between 200 and 400 billion stars. IC1101 has roughly 250 times more stars than our entire galaxy. If you tried to count the stars in IC1101 at a rate of 1 star per second, working 24 hours a day without rest, it would take you over 3 million years to count them all. The total mass of IC1101 is estimated at nearly 1 quadrillion solar masses. That's 1,000 trillion times the mass of our Sun. This includes not just stars, but also the diffuse gas between stars' stellar remnants like white dwarfs and neutron stars and black holes, and the vast dark matter halo that extends far beyond the visible galaxy. The gravitational influence of all this mass dominates the Abell 2029 cluster, holding together hundreds of other galaxies in its cosmic neighborhood. Now, here's something fascinating about IC1101's appearance. Unlike young blue galaxies with vigorous star formation, IC1101 glows with a golden yellow light. This color tells us something crucial about the galaxy's history and current state. The golden hue comes from old metal-rich stars that have been enriched with heavy elements forged in previous generations of stars. Some of these stars are 7 billion years old or more, meaning they formed when the universe was less than half its current age. The prevalence of old red and yellow stars indicates that IC1101 has long since passed its prime star-forming years. It's what astronomers sometimes call a red and dead galaxy, though that's perhaps unfairly dismissive. True, there's very little new star formation happening. The galaxy has exhausted most of its gas and dust, the raw materials needed to birth new stars. But those 100 trillion existing stars create a majestic ancient glow, like a cosmic bonfire of old embers. The galaxy is dying, yes, but dying with a magnificent luminosity that has persisted for billions of years. At the heart of IC1101 lurks something even more extraordinary than the galaxy itself. The central supermassive black hole is one of the most massive ever measured, weighing in at somewhere between 40 billion and 100 billion solar masses. Some models using different measurement techniques suggest it could be as high as 50 to 70 billion solar masses. These estimates place IC1101's black hole at or near the theoretical upper limits for black hole masses in our universe. Why would there be an upper limit? It has to do with the relationship between a black hole and its host galaxy. As matter falls toward a black hole, it forms an accretion disk, a swirling disk of superheated material orbiting the black hole before eventually crossing the event horizon. This process releases enormous amounts of energy in the form of radiation and sometimes powerful jets. This energy can actually blow away nearby gas, preventing additional matter from falling in. If a black hole grows too large, it becomes self-limiting. It produces so much energy that it clears out its surroundings and starves itself of fuel. IIT-1101's black hole is sometimes described as overmassive, bigger than theoretical models predict it should be given the galaxy's other properties. This suggests something unusual in the galaxy's history, perhaps an unusually efficient process of black hole mergers during the galaxy's formation, or an extended period of rapid accretion in the early universe when gas was more abundant. The black hole's mass is near what physicists call the cosmological limit, the maximum mass a black hole can achieve, given the age of the universe and the constraints of physics. The galaxy also has what's called an anomalously high mass-to-light ratio. In simple terms, this means IC1101 is darker than it should be for its mass. Much of the galaxy's mass is tied up in dark matter, and in stellar remnants, white dwarfs, neutron stars, and black holes that don't emit much light. This high ratio is another indicator of the galaxy's age. Over billions of years, the brightest stars have already died, leaving behind their dark remnants while contributing to the galaxy's gravitational mass. One of the most distinctive features of IC1101 is its diffuse core, the largest galactic core ever measured. Most elliptical galaxies have a relatively compact core where stars are densely packed, but IC1101's core is remarkably spread out with stars, distributed over an enormous volume. This diffuse core is likely the result of multiple major merger events in the galaxy's past. When galaxies merge, their central supermassive black holes eventually sink to the center and merge as well. But before that final merger, the black holes interact gravitationally with nearby stars, flinging some of them out to larger orbits. Over multiple merger events, this process hollows out the very center of the galaxy, creating that diffuse core we observe. Astronomers first began seriously studying EIC 1101 in the 1960s, when it was identified as a galaxy associated with radio emissions. But it wasn't until 1978 that astronomer Alan Dressler conducted a detailed analysis of the Abell 2029 cluster, and specifically focused on IC1101. His 1979 paper, dedicated solely to IC110, revealed something puzzling: a rising velocity dispersion profile. In simple terms, this means that stars farther from the galaxy's center were moving faster than expected, suggesting the presence of a massive dark matter halo, extending far beyond the visible galaxy. Throughout the 1980s and 1990s, IC1101 became a key target for studies of brightest cluster galaxies. Astronomers obtained detailed luminosity profiles, revealing that the galaxy's glow could be traced out for several hundred kiloparsecs from its center that's several 100,000 light-years. Some of this glow comes from intracluster light stars that don't belong to any particular galaxy, but instead drift through the space between galaxies in the cluster like cosmic nomads. The Chandra X-ray Observatory studied the Abell 2029 cluster in the early 2000s, revealing hot gas permeating the cluster. This gas, heated to millions of degrees, fills the space between galaxies and interacts with IC1101's gravitational field. The temperature and distribution of this gas provide clues about the cluster's history and the role IC1101 plays in shaping its environment. In 2017, observations with the Hubble Space Telescope allowed astronomers to peer into IC1101's inner regions with unprecedented clarity. These observations confirmed the enormous diffuse core and helped refine estimates of the central black hole's mass. Around the same time, redshift surveys of the cluster created a detailed map of galaxy velocities, allowing astronomers to model the cluster's dynamics and understand how IC1101 influences the motion of surrounding galaxies. Here's something worth pondering. IC1101 is not static. It's still growing. Smaller galaxies in the Abell 2029 cluster occasionally wander too close to this central giant and get torn apart by tidal forces. Their stars are absorbed into IIC110, one's outer halo, adding to its already enormous stellar population. This process, called tidal stripping, happens slowly over hundreds of millions of years. A smaller galaxy approaching IC110. One might first lose its outer stars, then gradually get stretched into long tidal streams, and finally merge completely with the giant. If we could watch IC1101 over a billion-year time span, we'd see it flickering with these minor merger events, each one adding a small percentage to its total mass. In the distant future, billions of years from now, IIC1101 will likely be even larger than it is today, having consumed many more of its neighboring galaxies. But there's a limit to this growth. Eventually, the expansion of the universe will carry distant galaxies out of reach, leaving IC1101 and the Abell 2029 cluster increasingly isolated. The question of whether intelligent life exists in EC110 is one that fascinates many people. With 100 trillion stars, surely some of them must have planets. And with so many planets, surely some must harbor life. The probability seems overwhelming. But here's the catch, IC110. One is an old, quiet galaxy with little star formation. Most of its stars formed billions of years ago. If intelligent civilizations arose on planets orbiting those stars, they've had billions of years to evolve and develop. Where are they? Could some of them have reached technological capabilities beyond our imagination? Or perhaps life is rare, even in a galaxy with 100 trillion stars. There's also the question of habitability. Many of IC1101's stars are old red giants or white dwarfs past their stable main sequence phase. The galaxy's core, with its intense stellar density and the radiation from the supermassive black hole, might be inhospitable to life. But the outer reaches, where stars are more spread out and conditions are calmer, could potentially harbor habitable worlds. We simply don't know, and at a distance of 1.15 billion light-years, we don't have the technology to find out. What we can say is this, IC110. One represents an endpoint in galaxy evolution. It's what happens when a galaxy grows through mergers over billions of years in the favorable environment of a rich galaxy cluster. It's consumed hundreds of smaller galaxies. Its supermassive black hole has grown to near the maximum possible mass. Its star formation has ceased. It's reached a state of maturity and quiescence that will persist for billions more years. And yet, for all its magnificence, IC1101's reign as the largest known galaxy came to an end in February 2022. The discovery of Alcyoneus forced us to reconsider what we mean by largest. IC1101 still has more stars spread over a greater volume of space. But Alcyoneus, with its enormous radio lobes extending 16 million light-years from end to end, encompasses a larger total structure. The two galaxies represent different kinds of cosmic giants, one massive and ancient one, ordinary at its core, but possessing the largest electromagnetic structure ever discovered. What could allow a relatively normal galaxy like Alcyoneus to create a structure that dwarfs even the stellar extent of IC1101? The answer lies in the extraordinary behavior of supermassive black holes when they're actively feeding, and in the particular environment that surrounds Alcyoneus. To understand how this new champion achieved its record-breaking size, we need to look at the powerful forces at work in its core. On a cold February night in 2022, astronomers at Leiden Observatory in the Netherlands were doing what astronomers do best, systematically combing through vast data sets, looking for patterns, anomalies, anything unusual that might reveal something new about the universe. They were analyzing the second data release from LOFAR, the Low Frequency Array, a network of radio telescopes spread across Europe. And buried in those terabytes of radio observations, they found something that shouldn't exist, a structure so vast that it challenged everything we thought we knew about the limits of galactic growth. The numbers seem wrong at first. The team led by Martijn Owe measured the radio emission extending from a galaxy and kept measuring and kept measuring. The lobes, those bubbles of energized plasma that radio galaxies create, just kept going. When they finally calculated the full extent, they were looking at a structure spanning 5.0 megaparsecs. In more comprehensible units, that's 3 million light-years from end to end. They had discovered Alcyoneus, and it had just claimed the title of largest known galaxy in the universe. If you're as captivated by this cosmic giant as I am, and you want to continue exploring these extraordinary discoveries together, please take a moment to like this video and subscribe to the channel. Your support helps us bring you these stories from the cutting edge of astronomical research. Let's put that measurement in perspective, because 16 million light-years is a number our minds weren't built to process. The previous record holder, IC1101, has a stellar extent of about 6 million light-years. Alcyoneus is roughly 2.7 times larger when measured from end to end. If you place the Milky Way at one end of Alcyoneus and Andromeda at the other, you'd need to line up more than 6,000 copies of the distance between them to span the full structure. It's not just large, it's incomprehensibly, almost absurdly large. The discovery itself was the result of technological advancement and careful analysis. LOFAR operates at some of the lowest radio frequencies used in astronomy, between 10 and 240 megahertz. These low frequencies are ideal for detecting age-diffuse plasma in giant radio lobes, because the synchrotron radiation from old electron populations peaks at these wavelengths. Higher frequency radio telescopes might miss these faint extended structures entirely. LOFAR's sensitivity to low-frequency radio emission, combined with its wide field of view, made it possible to detect Alcyoneus's enormous but diffuse lobes. But here's where the story takes an unexpected turn, and this is what makes Alcyoneus so scientifically intriguing. When the team examined the host galaxy at the center of this cosmic monster, they found something surprising. The galaxy itself is remarkably ordinary. It's an elliptical galaxy, yes, similar in type to IC1101, but it contains only about 240 billion times the mass of our Sun, roughly half the Milky Way's mass. For reference, IC1101 contains approximately 100 trillion solar masses. Alcyoneus's host galaxy is a relative lightweight, and the central supermassive black hole. It weighs in at about 400 million solar masses. That's certainly massive by everyday standards. You could fit about 100,000 of our Sun's mass into that black hole. But compared to other giant radio galaxies, it's actually on the smaller side. IC110. One's black hole is somewhere between 40 and 100 billion solar masses. Typical giant radio galaxies have black holes in the range of 10 to 100 billion solar masses. Alcyoneus's black hole is roughly 1/10 the mass we'd expect for a galaxy, creating such enormous radio lobes. This ordinariness is what makes the discovery so puzzling and so important. The researchers wrote in their paper that, beyond geometry, Alcyoneus and its host are suspiciously ordinary. The total low-frequency luminosity density stellar mass and supermassive black hole mass are all lower than those similar to those of the medial giant radio galaxies. In other words, by every measure except size, Alcyoneus is an average radio galaxy. It's not particularly bright at radio wavelengths. Its host galaxy isn't particularly massive. Its black hole isn't particularly large. So, how did it create the largest structure ever found? This question cuts to the heart of what we understand about galaxy evolution and the role of environment. If raw power, a massive black hole producing intense jets, isn't the determining factor, what is? The answer appears to be location, location, location. Just as in real estate, where you are matters enormously in cosmic architecture. The researchers hypothesized that Alcyoneus must reside in an unusually low-density region of the cosmic web. Remember our discussion about how radio lobes expand against the pressure of the intergalactic medium. If that external pressure is very low, then even modest jets can inflate lobes to enormous sizes given enough time. It's like inflating a balloon in a near vacuum versus inflating it underwater. The same amount of air creates vastly different balloon sizes depending on the external pressure. Reinout van Wieren, one of the co-authors of the discovery paper, noted that the next step in understanding Alcyoneus would be obtaining better measurements of its cosmic environment. They needed to map the distribution of galaxies around Alcyoneus, measure the density and temperature of the intergalactic medium in that region, and understand the large-scale structure. Only with that environmental context could they fully explain why this particular galaxy grew so large. The discovery also raises an intriguing possibility. If Alcyoneus achieved its record size through environmental factors rather than intrinsic power, might there be even larger giant radio galaxies lurking in existing survey data? Van Wieren and his colleagues suspect there are. The team is currently sifting through LOFAR survey data, looking for Alcyoneus's even larger cousins. The challenge is that the largest structures are also the faintest and most diffuse, making them difficult for automated detection algorithms to identify. They might be hiding in plain sight, waiting for the right analysis techniques to reveal them. Think about what this means. For decades, we assumed that extreme results required extreme causes. The largest galaxies must have the most massive black holes, the most powerful jets, the most extreme properties across the board. Alcyoneus demonstrates that assumption is wrong. Context matters. Environment matters. Sometimes being in the right place at the right time is more important than raw power. There's a lesson here that extends beyond astronomy. How often do we attribute success or achievement solely to intrinsic qualities? Talent, intelligence, strength, while overlooking the role of circumstances and environment? Alcyoneus reminds us that potential only manifests in context. The same galaxy in a different environment would look completely different. It's a humbling reminder that outcomes are shaped by the intersection of capability and circumstance. Let's examine the details of Alcyoneus' structure more closely. The radio lobes extend approximately 8 million light-years in each direction from the host galaxy. The lobes show the characteristic double-lobe structure of radio galaxies, one lobe on each side, aligned along the axis of the jets. The jets themselves launching from the black hole's poles maintain remarkable coherence across millions of light-years before finally decelerating and spreading into the lobes. The plasma in these lobes is incredibly diffuse. Despite containing the energy equivalent of billions of supernovae, that energy is distributed over such an enormous volume that the energy density is actually quite low. The lobes glow with radio emission as electrons spiral around magnetic field lines, but the actual number of particles per cubic meter is far lower than the best vacuum we can create in laboratories on Earth. These are cosmic ghosts, vast structures of extraordinary extent but ethereal substance. The age of the lobes can be estimated from the properties of the radio emission. The synchrotron radiation spectrum shows that the electron population has aged. The electrons have been losing energy over hundreds of millions of years. This tells us that Alcyoneus's jets have been active for at least several 100 million years, possibly longer. The jets have been running since before the dinosaurs appeared on Earth, steadily pumping energy and particles into these expanding bubbles. What's particularly fascinating is that the total radioluminosity of Alcyoneus is not exceptional. Some giant radio galaxies are much brighter at radio wavelengths, despite having smaller physical sizes. This further supports the environmental explanation. Alcyoneus isn't creating more radio emission than other giants, but its emission is spread over a larger area because the environment allowed greater expansion. The discovery of Alcyoneus also highlights the importance of multi-wavelength astronomy. The LOFAR observations revealed the radio lobes, but optical observations of the host galaxy showed its relatively modest stellar mass. X-ray observations would reveal the hot gas distribution in Alcyoneus' environment. Combining these different wavelengths gives us a complete picture that no single observation could provide. Now, let's consider the broader context. When we look at the distribution of giant radio galaxies across cosmic time, we see that they're relatively rare. Only about 5% of radio-loud active galactic nuclei grow lobes larger than 2.3 million light-years. And of those giants, only a small fraction reach sizes, like Alcyoneus. They represent the extreme tail of the size distribution outliers that tell us about the maximum sizes possible given the age and expansion rate of our universe. The rarity of objects like Alcyoneus means we're probably seeing something close to the maximum size that single galaxies can achieve. There are theoretical limits. The universe is only 13.8 billion years old, which constrains how long jets can have been running. The expansion of the universe works against the formation of ever larger structures. Dark energy drives galaxies apart, making it harder for individual galaxies to accumulate matter, or for their jets to reach across ever greater distances. But within those constraints, Alcyoneus represents an achievement. It's a galaxy that found itself in the right place, a low-density region where external pressure was minimal and ran its jets for hundreds of millions of years, creating a structure that spans a distance greater than most galaxy groups. It's a cosmic masterpiece of patient accumulation. What might we learn by studying Alcyoneus in detail? Understanding how such large structures form helps us understand the feedback processes between active galactic nuclei and their environments. The energy that Alcyoneus has pumped into the intergalactic medium over hundreds of millions of years has heated and stirred the gas in that region. This affects how gas cools and forms stars, not just in Alcyoneus itself, but in neighboring galaxies as well. Giant radio galaxies like Alcyoneus also serve as probes of the intergalactic medium. By studying how the radio lobes expand and interact with their surroundings, we can learn about the density, temperature, and composition of the gas between galaxies. This gas is hard to study directly because it's so diffuse, but its interaction with radio lobes leaves observable signatures. There's also the question of what Alcyoneus looks like now in its present state that we cannot observe. Remember, we're seeing it as it was 3 billion years ago. In the intervening time, has the central black hole shut down, causing the radio lobes to fade? Or are the jets still active, continuing to pump energy into even larger lobes? Has the galaxy merged with a neighbor, disrupting its structure? We can't know. The information about Alcyoneus' current state won't reach us for another 3 billion years. We are cosmic archaeologists studying ancient light. The discovery paper for Alcyoneus was published in Astronomy and Astrophysics in 2022, following peer review by other astronomers who verified the measurements and conclusions. The team's data and analysis methods are publicly available, allowing other researchers to confirm the findings independently. This is how science works. Discoveries must be reproducible and verifiable, not just announced. Since the announcement, Alcyoneus has captured the imagination of astronomers and the public alike. It's become the new benchmark, the new standard against which other large galaxies are measured. And it's inspired searches for even larger structures. Some teams are developing better algorithms for detecting diffuse low-surface brightness features in radio surveys. Others are proposing observations with next-generation telescopes that will be even more sensitive. The square-kilometer array currently under construction in South Africa and Australia will revolutionize radio astronomy when it comes online. With 50 times the sensitivity of current instruments, the SKA will almost certainly discover radio galaxies that dwarf even Alcyoneus. The question isn't whether we'll find larger structures, but how much larger they might be and what new puzzles they will present. But for now, Alcyoneus holds the crown. It's the largest single structure created by a galaxy that we've discovered so far. It's a monument to the power of supermassive black holes the influence of environment, and the patient processes that build structures over hundreds of millions of years. It's a reminder that the universe still holds surprises, that records are made to be broken, and that our understanding is always provisional, always subject to revision in light of new evidence. To truly understand why Alcyoneus grew so large, we need to dive deeper into the physics of how supermassive black holes create these jets, and how those jets interact with their environment over cosmic timescales. The mechanisms at work are some of the most extreme in the universe, involving energies and conditions we can barely imagine. Deep in the heart of Alcyoneus, there's a cosmic engine that has been running for hundreds of millions of years, pumping energy into space at a rate that dwarfs anything we can imagine on human scales. This engine, a supermassive black hole 400 million times the mass of our sun, is doing something extraordinary. It's creating two beams of plasma, each shooting outward at nearly the speed of light, carving channels through intergalactic space for millions of light years. These jets are the reason Alcyoneus holds the size record. But how does a black hole, an object from which nothing can escape, create jets that extend across such vast distances? The physics of active galactic nuclei and their jets represent some of the most extreme conditions in the universe. Temperatures reaching billions of degrees, magnetic fields millions of times stronger than Earth's, and energies that dwarf entire stellar explosions. Understanding how these cosmic monsters work helps us grasp not just why Alcyoneus is so large, but why the universe looks the way it does at the largest scales. If you're captivated by these extreme cosmic phenomena and want to continue exploring the universe's most powerful forces with us, please take a moment to like this video and subscribe to the channel. Your support fuels these deep investigations into the cosmos. Let's start at the very center, at the supermassive black hole itself. This black hole didn't spring into existence at 400 million solar masses. It grew over billions of years. In the early universe, seed black holes formed from the collapse of massive stars, or from direct collapse of dense gas clouds. These seeds, perhaps just a few hundred or thousand solar masses, initially sat at the centers of young galaxies, slowly accreting matter. As the galaxy grew through mergers, its black hole grew too, feeding on inflowing gas and merging with the black holes from smaller galaxies. But a black hole by itself is just an invisible point in space, its only property the warping of space-time around it. What makes an active galactic nucleus active is the accretion disk, the swirling disk of matter spiraling inward toward the black hole. Imagine a cosmic whirlpool, but instead of water, it's made of gas dust and shredded stars. As this material spirals inward, gravitational potential energy converts to kinetic energy and then to heat through friction between particles orbiting at different speeds. The inner regions of the accretion disk, close to the black hole, reach temperatures of millions or even billions of degrees. At these temperatures, atoms are completely ionized electrons, stripped away from their nuclei. The material glows intensely across the entire electromagnetic spectrum, from radio waves to gamma rays. In the most extreme cases, the energy released by matter falling into a supermassive black hole can outshine the entire surrounding galaxy of hundreds of billions of stars. The black hole, though tiny compared to the galaxy, becomes the brightest object in that region of space. Now here's where things get really interesting. Not all the matter in the accretion disk falls into the black hole. Some of it gets channeled into two narrow jets shooting out perpendicular to the disk, one from each pole. How does this happen? The answer involves magnetic fields, and the physics gets complex. But let me try to give you an intuitive picture. The gas in the accretion disk is ionized. It's a plasma, meaning it has charged particles moving around. Moving charged particles create magnetic fields, and those magnetic fields can exert forces on other charged particles. Near the black hole, these magnetic field lines get twisted and amplified by the rotation of the disk. Think of it like wringing out a wet towel. The twisting motion concentrates and strengthens the field lines. These twisted, intense magnetic field lines act like invisible rails or channels, guiding some of the plasma away from the accretion disk and out along the rotation axis of the black hole. The process is called the Blandford-Znajek mechanism, named after the physicists who first described it mathematically in 1977. Roger Blandford and Roman Znajek showed that a rotating black hole immersed in a magnetic field could extract rotational energy from the black hole itself and convert it into energy in the jets. The black hole spins, dragging space-time around it, an effect called frame dragging. The magnetic field threads through this spinning space-time, and the combination acts like a cosmic generator powering the jets. These jets are unlike anything we experience in everyday life. The plasma in the jets travels at 95 to 99% of the speed of light. At these velocities, special relativity becomes crucial. Time dilates, length contract, and the apparent brightness of the jets depends on the angle from which we view them. If a jet happens to be pointed almost directly at Earth, it appears much brighter than if we view it from the side due to relativistic beaming effects. The particles in the jets are mostly electrons and positrons matter and antimatter, along with some protons and heavier atomic nuclei. As these particles spiral along magnetic field lines in the jet, they emit synchrotron radiation. This is the same phenomenon that occurs in particle accelerators on Earth, but on an incomparably larger scale. Synchrotron radiation is what makes radio galaxies visible to radio telescopes. The jets themselves emit radio waves as the charged particles gyrate around magnetic field lines. Let me give you a sense of the energy involved. A typical active galactic nucleus might produce jets with a total power output of around 10 to the 45 ergs per second. To put that in perspective, that's equivalent to the energy of millions of supernovae going off continuously. If you could somehow capture just 1 second of a jet's energy output, it would be enough to power human civilization at current consumption levels for billions upon billions of years. The amount of energy being pumped into these jets is staggering beyond human comprehension. As the jets plow through space, they eventually slow down. This happens far from the black hole millions of light years away, where the jets run into the thin gas that fills the space between galaxies, the intergalactic medium. The jet material spreads out, forming what we call radio lobes. These lobes are vast bubbles of relativistic plasma filled with energetic particles and tangled magnetic fields glowing with radio emission. The lobes of Alcyoneus each extend about 8 million light-years from the galaxy's center, making the total structure 16 million light-years across. Think of it this way. If the jets are like fire hoses spraying water at high pressure, the lobes are like the pools of water that form where the spray hits the ground and spreads out. Except in this case, the hoses have been running for hundreds of millions of years, and the pools are larger than the distance between galaxies. The synchrotron radiation from radio lobes has a characteristic spectrum more intense at lower frequencies and falling off at higher frequencies. This is why radio telescopes tuned to low frequencies like LOFAR are so good at detecting giant radio galaxies. The emission from the lobes is relatively weak at any given frequency, but spread over such an enormous volume, the total radio luminosity is immense. LOFAR's sensitivity to low-frequency radio waves allowed it to detect Alcyoneus's lobes where previous surveys had missed them. One of the fascinating aspects of radio galaxies is their time scale. These jets don't operate for just a few years, or even a few million years. Some active galactic nuclei maintain their jets for hundreds of millions of years, possibly even billions. During that time, the black hole has to continually feed on infalling matter to power the jets. This requires a steady supply of gas, either from the interstellar medium within the galaxy or from gas falling in from intergalactic space. But jets don't run forever. Eventually, the fuel supply dwindles. Perhaps the galaxy runs out of cold gas, or perhaps the energy output from the active nucleus itself blows away nearby gas, cutting off the fuel supply. When the jets shut down, the radio lobes gradually fade. The energetic particles lose energy through synchrotron radiation and other processes, and without fresh input from the jets, the lobes dim over millions of years. What remains are ghost remnants, faint diffuse structures, visible only in the most sensitive radio surveys. Interestingly, not all active galactic nuclei produce jets. Some black holes accrete matter, but don't launch jets or produce very weak jets that don't extend far. The difference seems to come down to the black hole's spin and the strength and configuration of the magnetic fields in the accretion disk. A rapidly spinning black hole with strong, well-organized magnetic fields threading through it is most likely to produce powerful, sustained jets. The details are still being worked out by theorists and observational astronomers. There's another crucial factor: the rate at which the black hole accretes matter. Feed a black hole too much matter too quickly, and the accretion disk becomes thick and turbulent, disrupting the magnetic fields needed for jet formation. Feed it too slowly, and there isn't enough energy to power strong jets. There's a sweet spot, what astronomers call the radiatively inefficient accretion flow regime, where jets are most efficiently produced. In this regime, the accretion disk is geometrically thick but optically thin, meaning it's puffed up but transparent, allowing magnetic fields to be amplified effectively. Now, you might wonder if only about 5% of radio-loud active galactic nuclei become giant radio galaxies with lobes extending more than 3 million light-years. What makes those 5% special? Why do some jets create lobes that extend to record-breaking distances while most stay relatively small? The answer, as we'll see, has less to do with the black hole or the jets themselves, and more to do with the environment surrounding the galaxy. Let me share a comparison that might help crystallize this. Think of trying to inflate a balloon. If you blow up a balloon in a high-pressure environment, say deep underwater, the balloon stays small because the surrounding water pressure resists expansion. But inflate that same balloon in a low-pressure environment, like high on a mountain or in space, and it expands much more easily. The amount of air you're putting in might be the same, but the external pressure determines the final size. Radio lobes work similarly. The jets inject energy and particles into the lobes, but the lobe's expansion is resisted by the pressure of the intergalactic medium, the thin gas filling space around the galaxy. In a dense, high-pressure environment, like the center of a rich galaxy cluster, the lobes can't expand as much. But in a low-density, low-pressure environment, the same jet power can inflate lobes to much larger sizes. This is likely the key to understanding Alcyoneus. The total energy contained in Alcyoneus's radio lobes is equivalent to billions of supernovae. Yet this energy was deposited over hundreds of millions of years by jets that, while powerful, aren't exceptional compared to other radio galaxies. What's exceptional is how far that energy was able to spread, how large the lobes were able to grow before the expansion slowed. The environment around Alcyoneus must be unusually rarefied, with very low gas density allowing the lobes to reach record-breaking proportions. This brings us to a profound realization: the largest structures in the universe aren't necessarily created by the most powerful forces. Sometimes size is as much about opportunity and environment as it is about raw power. Alcyoneus achieved its record not because its black hole is exceptional. Remember, it's actually smaller than most radio galaxy black holes, but because it happened to form in the right place where conditions allowed unimpeded expansion over cosmic timescales. There's a beautiful lesson here about the universe's diversity. We often think of extremes as requiring extreme causes. The hottest stars must be the most massive, the brightest galaxies must have. The most stars, the largest structures must be powered by the most energetic processes. But nature is subtler than that. Context matters. Environment matters. The interaction between an object and its surroundings can be just as important as the object's intrinsic properties. Have you ever felt like circumstances beyond your control shaped your path more than your own abilities? There's a cosmic parallel here. Even galaxies are products of both their internal dynamics and their environmental context. Alcyoneus reminds us that sometimes being in the right place at the right time matters as much in the cosmos as it does in life. The physics we've explored, accretion disks, magnetic fields, relativistic jets, synchrotron radiation, these are the mechanisms that create giant radio galaxies. But to understand why Alcyoneus specifically became the largest we need to look beyond the galaxy itself and examine the cosmic neighborhood in which it resides. What's special about the space around Alcyoneus that allowed its lobes to expand to such unprecedented sizes? Picture the universe not as a random scattering of galaxies in empty space, but as an intricate cosmic web, filaments of galaxies stretching across hundreds of millions of light years, connecting massive clusters at the intersections with vast voids in between containing almost nothing. This web structure isn't random. It's the result of how matter distributed itself under gravity over billions of years following the Big Bang. And where a galaxy happens to find itself in this web can determine whether it grows to record-breaking proportions or remains unremarkable forever. Alcyoneus didn't achieve its extraordinary size through brute force alone. Its location in the cosmic web, its cosmic address, if you will, played a crucial role. Understanding this environmental factor helps us solve one of the most puzzling aspects of this giant, why a relatively ordinary galaxy managed to create such an extraordinary structure. If this exploration of how cosmic environment shapes galactic destinies fascinates you, please consider liking this video and subscribing. These investigations into the hidden factors that shape our universe take time and care to develop, and your support means we can continue this journey together. When Reinout van Wieren and his colleagues at Leiden Observatory analyzed Alcyoneus, they immediately recognized that the galaxy itself wasn't special. The central black hole wasn't exceptionally massive. The host galaxy wasn't particularly bright or heavy. By all accounts, Alcyoneus should have been just another radio galaxy. But its environment, that was a different story. Van Wieren hypothesized that Alcyoneus must reside in an unusually low-density region of the cosmic web, where the thin gas between galaxies exerts minimal pressure against the expanding radio lobes. Let's explore what this means. The space between galaxies isn't truly empty. It's filled with what astronomers call the intergalactic medium, a diffuse gas consisting primarily of hydrogen and helium, the primordial elements formed in the Big Bang. This gas is extraordinarily thin, with densities far lower than the best vacuum we can create in laboratories on Earth. In the voids between galaxy filaments, there might be just one atom per cubic meter of space. Even in the filaments themselves, the density is only slightly higher. But small as these densities are, they matter. When a radio lobe tries to expand, it has to push against this intergalactic medium. The gas exerts pressure resisting the expansion. Think of it like blowing a bubble underwater versus blowing one in air. Underwater, the higher pressure of the water keeps the bubble small. In air with lower pressure, the same amount of breath creates a larger bubble. For radio lobes, the density and temperature of the surrounding medium determine the external pressure, which in turn determines how large the lobes can grow for a given amount of energy input from the jets. Astronomers have a mathematical relationship that describes this balance. It's called the pressure equilibrium condition. The internal pressure of the radio lobe created by the hot energetic particles and magnetic fields inside must balance against the external pressure of the intergalactic medium. If the external pressure is low, the lobe can expand to larger sizes before reaching equilibrium. If external pressure is high, the lobe stays smaller, even if the jets continue pumping in energy. Galaxy clusters have the highest gas densities outside of galaxies themselves. The space between galaxies in a rich cluster, like Abell 2029, where IC1101 resides, contains hot gas heated to tens of millions of degrees by the gravitational energy of the cluster. This hot gas is detectable through its X-ray emission, and it exerts significant pressure. A radio galaxy in such an environment faces strong resistance to lobe expansion. The lobes might only extend a few 100,000 light years before the cluster gas stops them from growing further. Contrast that with a galaxy residing in a cosmic void, or on the outskirts of a filament where gas density is minimal. Here, the intergalactic medium exerts very little pressure. Radio lobes can expand much more easily, reaching sizes of several million light years or more. This appears to be the case with Alcyoneus. Preliminary observations suggest it resides in a relatively isolated region, not in the dense environment of a galaxy cluster. But there's more to the environmental story than just gas density. The structure of the cosmic web itself matters. Galaxies and filaments are connected by streams of gas flowing along the filament structures. These flows can affect how jets propagate. If a jet happens to be aligned with a filament, it might travel farther because it's moving through a relatively lower density channel. Conversely, a jet pointing perpendicular to a filament would encounter denser gas and be slowed down more quickly. The cosmic web formed through a process cosmologists call gravitational instability. In the early universe, matter was distributed almost uniformly, but with tiny density fluctuations regions that were slightly denser or slightly less dense than average. Over time, gravity amplified these fluctuations. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their denser neighbors, becoming more rarefied. This feedback process, operating over billions of years, created the web structure we see today, dense nodes, where galaxy clusters form filaments connecting the nodes and vast voids with very little matter. The voids are particularly interesting environments. They're the largest structures in the universe, spanning 50 to 100 million light years or more. Within a void, galaxy formation is suppressed because there simply isn't enough matter. The few galaxies that do form in voids tend to be small and isolated. But for a radio galaxy, a void environment is ideal for growing large radio lobes. There's almost nothing to push back against the expansion. Could Alcyoneus be located in or near a cosmic void? The research team is still investigating this question. Measuring the precise environment around a galaxy 3 billion light years away isn't easy. You need to map the distribution of nearby galaxies, measure the density of the intergalactic medium, and understand the large-scale structure in that region. This requires extensive follow-up observations with multiple telescopes. Van Wieren and his colleagues have noted that understanding Alcyoneus's environment is the next crucial step in explaining its size. They're conducting surveys to map the galaxy distribution around Alcyoneus and measure the properties of the surrounding medium. Only with this environmental context can they fully explain why Alcyoneus grew so large, while other radio galaxies with similar properties stayed smaller. There's a concept in ecology called the competitive exclusion principle, the idea that two species competing for the same resources can't coexist indefinitely in the same niche. One will eventually outcompete the other. Galaxies don't compete in quite the same way, but there's an analogous effect. In dense environments like galaxy clusters, galaxies compete for gas. The largest galaxies sitting at the bottom of the gravitational potential will attract and hold onto more gas. Their radio lobes face high pressure from the cluster medium. In sparse environments, there's no competition, plenty of space for everything, and low pressure allows structures to grow large. Think about how this mirrors patterns in the natural world. The largest trees in a forest are often found where they have room to spread, not in dense thickets where they compete for sunlight and nutrients, but in clearings or on the forest edge. The largest animals often need vast territories with ample resources and few competitors. Alcyoneus, in cosmic terms, may have found itself in a spacious clearing rather than a crowded thicket. Let me give you another terrestrial analogy that might help. Imagine two identical balloons filled with the same amount of helium. Release one at sea level, where atmospheric pressure is high. It rises, but as it ascends, the balloon expands because external pressure decreases with altitude. However, it doesn't get too large before reaching an equilibrium altitude where the helium's buoyancy matches the atmospheric density. Now, release the second balloon from the top of Mount Everest, where atmospheric pressure is already low. This balloon can expand much more because it started in a lower pressure environment. Radio lobes are similar. Those that form in low pressure environments can achieve larger final sizes. The history of understanding cosmic environments' role in galaxy evolution stretches back several decades. In the 1970s and 1980s, astronomers noticed that galaxies in clusters looked different from galaxies in the field. Less gas, less star formation, more elliptical morphologies. This led to the realization that environment matters. Galaxies aren't isolated island universes. They're influenced by their neighborhoods. Subsequent observations revealed environmental effects at multiple scales. On small scales, close galaxy pairs often show signs of interaction. Tidal distortions triggered star formation. On intermediate scales, galaxy groups show different properties than isolated galaxies. On large scales, the position in the cosmic web determines gas accretion rates and merger histories. Radio galaxies fit into this environmental paradigm. Their jets and lobes interact with the surrounding medium, and that interaction determines the observable properties. One of the persistent mysteries in extragalactic astronomy is why giant radio galaxies are rare. Only about 5% of radio-loud active galactic nuclei qualify as giant radio galaxies with projected sizes exceeding 3 million light-years. Given that many galaxies have similar black hole masses and accretion properties, why don't they all produce giant lobes? The environmental explanation provides an answer. Most radio galaxies reside in environments that prevent their lobes from expanding to giant sizes. Only those lucky few that form in low-density regions can achieve giant status. This has implications for how we search for and find giant radio galaxies. If environment is the key factor, we should focus searches on regions away from galaxy clusters, in the outskirts of filaments, in walls, and especially near voids. Van Weeren's team suspects there might be even larger radio galaxies lurking in existing survey data, overlooked because they're so diffuse and faint that they blend into the background noise. More sensitive surveys with better algorithms for detecting extended low surface brightness features might reveal additional giants. There's also the question of intra-cluster light, the diffuse glow of stars that don't belong to any particular galaxy, but instead wander through the space between cluster galaxies. These stars are the remnants of tidal disruption events, where galaxies passing through the cluster get torn apart by gravitational forces. IC1101, sitting at the center of Abell 2029, is surrounded by intracluster light. Studies in 2019 and 2020 surveyed 170 local galaxy clusters to understand this intracluster light and how it relates to brightest cluster galaxies. The intracluster light tells us about the cluster's merger history. More intracluster light means more tidal disruption, which means a more dynamically active cluster. It's a fossil record written in starlight, revealing the violent history of galaxy interactions. For IC110, the extensive intracluster light confirms that it has been feasting on smaller galaxies for billions of years, growing larger with each meal. Alcyoneus, by contrast, likely has far less intracluster light if it's in a sparse environment. Fewer nearby galaxies means fewer tidal interactions and less disruption. The galaxy may have grown through a few major mergers in its past, but its environment doesn't provide the constant stream of smaller galaxies that AC1101 enjoys. What it lacks in merger opportunities, however, it compensates for with room to spread its radio lobes. Consider the cosmic real estate analogy. IC1101 is like a mansion in a crowded, wealthy city, impressive in its own right, with access to resources and surrounded by valuable neighbors, but constrained by its urban environment. Alcyoneus is like a ranch in the countryside. The main house might be modest, but the property extends as far as the eye can see. Both are impressive, but in different ways, and for different reasons. Can you think of times when your circumstances allowed you to achieve something you couldn't have accomplished elsewhere? or times when constraints of your environment limited what you could do despite your best efforts. Galaxies face similar realities. Potential alone doesn't determine outcomes. Context matters profoundly. The next step in Alcyoneus research involves detailed environmental mapping. Astronomers need to measure the gas density around the galaxy using X-ray observations and radio observations of neutral hydrogen. They need to map the distribution of neighboring galaxies to understand the large-scale structure. They need to determine whether Alcyoneus is truly in a void-like environment or perhaps in a filament that provides just the right conditions for lobe expansion. These environmental studies have broader implications beyond explaining one record-breaking galaxy. Understanding how environment affects radiolobe growth helps us understand feedback processes, how active galactic nuclei inject energy into the intergalactic medium, and regulate galaxy and cluster evolution. The energy pumped into space by jets and lobes can heat the surrounding gas, preventing it from cooling and forming stars. This feedback is thought to be crucial in explaining why the most massive galaxies have stopped forming stars. The interplay between galaxies and their environments is one of the central themes in modern astrophysics. Galaxies shape their environments through stellar winds, supernova explosions, and active galactic nucleus feedback. Environments shape galaxies through gas accretion, tidal interactions, and pressure effects. It's a dynamic two-way relationship playing out over cosmic time. Alcyoneus offers a particularly clear example of this relationship, a galaxy whose most distinctive feature exists only because its environment permitted it. As we step back from the immediate environment around Alcyoneus and consider the larger context, a new dimension of wonder emerges. We're not just looking at a galaxy as it exists now. We're looking at a galaxy as it was 3 billion years ago when the light we're detecting began its journey across space. That journey spans a significant fraction of cosmic history, and it raises profound questions about time, distance, and perspective in an expanding universe. When you look at Alcyoneus through a radio telescope, you're not seeing it as it is right now. You're seeing it as it was 3 billion years ago, long before our solar system existed, before Earth formed, before the first stirrings of life in our cosmic neighborhood. The light and radio waves we detect tonight began their journey across space when the universe was barely 10 billion years old, still in what we might call its middle age. This time delay transforms every astronomical observation into an act of cosmic archaeology, and it raises a fascinating question. What might Alcyoneus look like right now in its present state that we cannot see? The vast gulfs of space and time that separate us from distant galaxies do more than just delay information. They fundamentally change how we understand cosmic history and our place within it. When we observe the universe at different distances, we're simultaneously looking at different epochs, building a timeline of cosmic evolution from fragments scattered across billions of light years. If these reflections on cosmic time and perspective resonate with you, I'd be grateful if you'd like this video and subscribe. Exploring these profound questions about time and space is what drives us, and your support allows us to continue this journey of discovery. Let's start with a basic but mind-bending fact. Light travels at 186,282 miles per second, or about 300,000 kilometers per second. This is the cosmic speed limit, the fastest that information can travel through the universe. Nothing with mass can reach this speed, and even light itself takes time to traverse cosmic distances. A light year. The distance light travels in 1 year is about 5.88 trillion miles, or 9.46 trillion kilometers. Alcyoneus is 3 billion light years away, meaning the radio waves we detect traveled approximately 18 sextillion miles to reach us. That's 18, followed by 21 zeros. During the 3 billion years those radio waves traveled through space, extraordinary changes occurred on Earth. 3 billion years ago, our planet was a dramatically different world. The continents were arranged in completely unfamiliar configurations. the atmosphere contained far less oxygen than today. Life existed only as single-celled organisms, bacteria and archaea living in oceans, and possibly forming stromatolite structures in shallow waters. There were no plants, no animals, no fungi. The most complex life forms were colonial bacteria. Fast forward through those 3 billion years. Photosynthesis evolved, gradually enriching the atmosphere with oxygen. Eukaryotic cells with nuclei emerge possibly through the merger of simpler cells. Multicellular life appeared. Plants colonized land. Animals diversified into an astonishing variety of forms. Dinosaurs rose and fell. Mammals evolved and spread across continents. Primates appeared, and eventually one lineage became us. Our entire species, Homo sapiens, has existed for only about 300,000 years, a mere 1/10,000th of the time it took light from Alcyoneus to reach us. Meanwhile, what was happening to Alcyoneus during those 3 billion years, we don't know. We can't know. The information about its current state hasn't reached us yet. We see it frozen in time as it was in that ancient epoch. Its jets might still be active, pumping energy into those enormous radio lobes. Or perhaps they shut down 1 billion years ago, and the lobes are now fading remnants. The galaxy might have merged with a neighbor, transforming its structure. Or it might look much the same, its evolution proceeding slowly over such vast timescales. This is one of the profound limitations of astronomy. We observe the universe through what's essentially a time machine, but it only works in one direction, backwards. We can look into the past with exquisite detail, but we cannot see the present state of distant objects. Every galaxy we observe is a ghost, an image from a time long past. The farther away the galaxy, the older the ghost. The concept becomes even more intriguing when we consider the universe's expansion. Space itself is expanding, carrying galaxies away from each other. When the radio waves left Alcyoneus 3 billion years ago, the universe was smaller than it is today. As those waves traveled through space itself was stretching, and the waves stretched along with it. This stretching shifts the waves to longer wavelengths, a phenomenon called cosmological redshift. Radio astronomers can measure this redshift to determine how far away a galaxy is and how fast space is expanding. The expansion of the universe means that Alcyoneus is actually farther away from us now than it was 3 billion years ago when the light we're seeing left it. In fact, it's currently about 3.4 billion light-years away due to the expansion of space during the light travel time. This might seem paradoxical. How can something be farther away than the time it took light to reach us? But remember, space was expanding while the light was traveling. The galaxy was receding from us, even as its light was approaching us. Let's explore the timeline of galaxy evolution to put Alcyoneus and IC1101 in context. In the early universe, just a few 100 million years after the Big Bang, the first stars ignited in small proto-galaxies. These early galaxies were nothing like the giants we see today. They were scrappy, irregular collections of hot young stars, intensely forming new stars from abundant gas. The universe was a more violent place then, with galaxy collisions happening frequently in the denser early cosmos. As billions of years passed, these small galaxies merged into larger ones. The merger rate declined as the universe expanded and galaxies spread out. By about 7 billion years after the Big Bang, roughly the epoch when we're seeing Alcyoneus, many massive elliptical galaxies had already formed. The universe's star formation rate was declining from its peak several billion years earlier. Galaxy clusters were well established with their giant central galaxies already in place. IC1101, being 1.15 billion light-years away, is closer to us in both space and time. We see it as it was 1.15 billion years ago, still ancient by human standards, but much more recent in cosmic terms. At that epoch, about 12.6 billion years after the Big Bang, the universe looks similar to how it does today. Star formation had slowed significantly. Most large galaxies had already assembled. the cosmic web structure was fully developed. Think about this temporal perspective. When we compare Alcyoneus and IC 1101, we're not just comparing two galaxies at different distances, we're comparing galaxies at different epochs in cosmic history, separated by nearly 2 billion years. Alcyoneus, as we see it, dates from when the universe was about 10.8 billion years old. IC 1101, as we see it, dates from when the universe was about 12.6 billion years old. We're witnessing different chapters in the story of cosmic evolution. One of the fascinating aspects of modern cosmology is how we use observations at different distances and thus different times to piece together the history of the universe. We can't watch a single galaxy evolve over billions of years. Our human lifespans and even our civilization's entire existence are far too short. But we can observe galaxies at many different distances, effectively sampling different ages. And from these snapshots, construct a timeline of how galaxies evolve over cosmic history. Imagine trying to understand human aging by looking at a large crowd of people of different ages all at once. You can't watch a baby grow up, but by comparing infants to children, to teenagers, to adults, to elderly individuals, you can piece together the life cycle. Astronomers do something similar, with galaxies observing them at redshifts ranging from nearly zero nearby galaxies we see, almost as they are today, to redshifts greater than 10 galaxies seen, as they were less than a billion years after the Big Bang. These observations have revealed a consistent story. In the early universe, galaxies were smaller, more irregular in shape, and more actively forming stars. The gas content was higher because less of it had been converted to stars. Galaxy mergers were more common. As time progressed, mergers built larger galaxies. Star formation gradually declined as gas was consumed or heated to temperatures too high for star formation. Elliptical galaxies, the products of major mergers, became more common among massive galaxies. By the present day, or at least the most recent epoch we can observe, the most massive galaxies are typically red, quiescent ellipticals sitting at the centers of galaxy clusters. They've exhausted their star-forming gas. Their central black holes have grown massive through accretion and mergers. They're approaching an end state, at least for the current cosmic epoch. IC 1101 is a perfect example of such a galaxy in its mature quiescent state. But what about the far future? What will happen to these cosmic giants over the next billions of years? Here we must turn to theoretical predictions and simulations, because we obviously can't observe the future. The models suggest several possible fates depending on the galaxy's environment. For galaxies and clusters like IC 110, the future involves continued growth through the slow accumulation of smaller galaxies and intracluster stars. Over the next tens of billions of years, IC 1101 might double or triple in mass as it gradually consumes its neighbors. The cluster itself might merge with neighboring clusters, creating even larger structures. Eventually, in the very far future, perhaps 100 billion years from now, most of the galaxies in the cluster will have merged into a single gargantuan elliptical galaxy, a sort of super IC 1101. But there's a catch. The expansion of the universe driven by dark energy is accelerating. This means that eventually, on time scales of hundreds of billions of years, galaxy clusters will become isolated islands in an expanding void. Clusters that haven't merged by then never will, because the space between them will be expanding faster than they can move through space. Each cluster will evolve in isolation, unable to interact with others. In these isolated clusters, stellar evolution continues. Stars burn out one by one. The most massive stars, which burn brightest and fastest, have already died in the present epoch. But even the smallest, longest-lived red dwarf stars will eventually exhaust their fuel in a few trillion years. As star formation ceases no new gas to form stars, the galaxies will gradually fade, populated only by stellar remnants. White dwarfs, neutron stars, and black holes. In this far future, perhaps 10 trillion years from now, C110, 1 will be a dark, cold collection of stellar remnants orbiting its central supermassive black hole. The universe will be a lonely place, other clusters long since invisible beyond the cosmic horizon, unreachable due to the expansion of space. The cosmic web will have dissolved into isolated islands, each containing the merger remnants of what were once hundreds of galaxies. For Alcyoneus, the fate might be somewhat different if it truly resides in a low-density environment. Without the gravitational attraction of a rich cluster, it might not accumulate as much additional mass. Its radio lobes, if they're still active, might eventually fade as the central black hole runs out of fuel. The galaxy will evolve more quietly without the dramatic mergers that cluster galaxies experience. It might remain a relatively isolated giant, a cosmic hermit in the expanding void. The Milky Way faces a different but equally interesting future. In about 4 billion years, we're due for a collision with Andromeda, our neighboring large spiral. This merger will scramble both galaxy structures, creating a large elliptical galaxy that some astronomers have whimsically nicknamed Milkomeda. The merger will trigger bursts of star formation as gas clouds collide. Our sun by then, an aging red giant, will likely be flung into a new orbit, possibly in the outskirts of the merged galaxy. The night sky for any observers on surviving planets will look completely different. Later, perhaps 6 billion years from now, Milkomeda might merge with other members of our local group, smaller galaxies like the Triangulum galaxy and various dwarf galaxies. The final product will be a large elliptical galaxy, possibly resembling a scaled-down version of IC1101. Our local group will become a single galaxy isolated from other galaxy groups and clusters by the expanding space between them. Have you ever thought about how your perspective changes when you zoom out to longer timescales? Daily concerns that seem urgent fade to insignificance when viewed across years or decades. Similarly, the apparent permanence of cosmic structures dissolves when we consider billions or trillions of years. Stars, galaxies, even clusters, all are temporary configurations of matter, slowly evolving toward eventual dissolution. There's something both humbling and oddly comforting in this cosmic perspective. We live in a special time, a universe old enough to have built complex structures like galaxies and planetary systems and life, but young enough that stars still shine and galaxies still sparkle with new star formation. We're in the stelliferous era, when the universe is dominated by stars. This era began a few 100 million years after the Big Bang and will last perhaps 100 trillion years. After that comes the degenerate era, dominated by stellar remnants, then the black hole era, and finally the dark era, when even black holes have evaporated and the universe contains only diffuse particles and radiation. Our observations of Alcyoneus and C1101 are snapshots from different moments in cosmic history, both falling within this stelliferous era. They show us what galaxies look like at different stages of maturity, different environments, different paths through the space of possibilities. They're data points in the grand story of cosmic evolution. The story of these galaxies doesn't end with our observations and our attempts to understand what they mean. Astronomy is an ongoing enterprise with new discoveries constantly challenging and refining our understanding. Even as we've been exploring the physics and history of these cosmic giants, astronomers have been asking, could there be even larger structures waiting to be discovered? Right now, as we speak, astronomers are sifting through massive data sets from radio telescopes around the world, searching for faint signatures that might reveal even larger cosmic giants hiding in plain sight. Alcyoneus held the record for less than a year before its discovery was announced in February 2022. But that doesn't mean it will hold the record forever. In fact, the team that discovered it strongly suspects there are bigger cousins lurking in the data, waiting for the right algorithms and the right eyes to find them. The search for the universe's largest structures is far from over. The hunt for giant radio galaxies represents one of the most exciting frontiers in observational astronomy, a field where each new survey brings the possibility of finding something that rewrites the record books and challenges our understanding of what's possible in the cosmos. If the ongoing search for cosmic discoveries excites you as much as it does me, please take a moment to like this video and subscribe. Supporting this channel helps us bring you the latest findings as they emerge from observatories around the world. When Martin Owe and his team discovered Alcyoneus in the LOFAR survey data, they weren't specifically looking for the largest galaxy. They were conducting a systematic search for giant radio galaxies in general, applying algorithms to the enormous dataset produced by LOFAR's survey of the northern sky. The algorithm flagged Alcyoneus as a candidate based on its extended radio emission, and follow-up analysis confirmed its extraordinary size. But here's the key insight: Alcyoneus was already in the data. It had been observed, recorded, stored on hard drives. It just hadn't been recognized for what it was until someone looked at the data in the right way. This raises a tantalizing possibility. How many other giant radio galaxies are hiding in existing survey data, overlooked because they're too faint, too diffuse, or too unusual in appearance for automated detection algorithms to flag them? Reinout van Wieren, one of the co-authors of the Alcyoneus discovery paper, explicitly stated that the team believes there are likely even larger radio galaxies lurking in their surveys. They're currently developing more sophisticated search techniques to find them. The challenge with finding the largest radio galaxies is partly technical and partly conceptual. On the technical side, these objects are incredibly faint. Their radio emission is spread across such vast areas of sky that the surface brightness, the brightness per unit area, is extremely low. It's like trying to see a dim light bulb in a very large room versus a bright light bulb in a small room. The total light output might be similar, but the spread out light is much harder to detect against background noise. Radio telescopes detect electromagnetic radiation at wavelengths ranging from millimeters to meters, much longer than visible light. This long wavelength means radio telescopes need to be very large or work together as arrays to achieve good resolution. LOFAR, the low-frequency array, operates at some of the lowest frequencies used in radio astronomy, between 10 and 240 megahertz. These low frequencies are ideal for detecting the age of diffuse plasma in giant radio lobes, but the data processing is computationally intensive and requires careful removal of interference from terrestrial radio sources. The conceptual challenge involves knowing what to look for. Giant radio galaxies don't always have obvious bright cores or clear boundaries. Their lobes can be irregular in shape, with filaments and tendrils extending in multiple directions. Sometimes only one lobe is visible, with the other hidden behind the core or pointing away from Earth. Some giant radio galaxies have what are called X-shaped morphologies, with additional wings extending in directions perpendicular to the main lobes. These unusual structures can confuse automated detection algorithms designed to look for more standard double-lobed sources. Survey limitations also play a role. LOFAR surveyed the northern sky, but what about the southern sky? The Murchison Wide Field Array in Australia and other southern hemisphere radio telescopes are conducting their own surveys, and they might reveal giant radio galaxies in southern regions of sky that LOFAR couldn't observe. There's an inherent bias in our discovery of cosmic objects. We can only find what our instruments can detect, and different instruments have different strengths and limitations. Distance bias is another factor. Alcyoneus is 3 billion light-years away, which is relatively nearby in cosmological terms. Radio galaxies at greater distances, say 5 or 6 billion light-years away, would appear smaller on the sky, even if their physical size were identical, and their radio emission would be correspondingly fainter. We might be missing even larger structures, simply because they're too far away for current surveys to detect reliably. There's also the question of orientation. Radio lobes extend along the axis of the jet, perpendicular to the accretion disk. If we happen to view a giant radio galaxy from an angle where the lobes are foreshortened, compressed along our line of sight, it will appear smaller than its true size. The projected size we measure is always less than or equal to the true three-dimensional size. Alcyoneus' measurement of 16 million light-years is its projected size on the sky. The true size accounting for the galaxy's orientation in space is at least that large and possibly larger. Statistical studies of giant radio galaxies suggest that only about 5% of radio-loud active galactic nuclei grow lobes larger than 2.3 million light-years. If we apply this percentage to the total population of radio galaxies in the observable universe, there should be tens of thousands of giant radio galaxies and perhaps hundreds or even thousands that are larger than Alcyoneus. Most of them are simply too distant or too faint to have been detected yet. The next generation of radio telescopes promises to revolutionize this field. The Square Kilometre Array, currently under construction in South Africa and Australia, will be the world's largest radio telescope when completed. With a collecting area of 1 square kilometer spread across thousands of individual antennas, the SKA will be 50 times more sensitive than any existing radio telescope. It will detect faint distant radio sources that are completely invisible to current instruments. The SKA will also have much better resolution, the ability to distinguish fine details. This combination of sensitivity and resolution is crucial for finding and studying giant radio galaxies. The telescope will be able to detect the diffuse lobes while also resolving internal structure, helping astronomers understand the physics of how these lobes form and evolve. First science observations from the SKA are expected in the late 2000s and 20s, and within a few years of operation, it's likely to discover numerous new record-breaking giants. Beyond just finding larger galaxies, these new observations will help answer fundamental questions. Why do some radio galaxies grow to giant sizes while most don't? Is it purely environmental, or are there intrinsic properties of the black hole or galaxy that matter? How does the energy from jets and lobes affect the surrounding intergalactic medium? What can the distribution of giant radio galaxies tell us about the structure of the cosmic web? Let's consider some of the other largest categories in astronomy, because size can be measured in many ways. We've talked about Alcyoneus as the largest by total structure, and IC1101 as the largest by stellar extent. But there are other candidates depending on how you define largest. UGC 2885, sometimes called Rubin's Galaxy, after astronomer Vera Rubin, who studied it extensively, is the largest known spiral galaxy. It spans about 832,000 light-years, in diameter 8 times larger than the Milky Way, and contains about 1 trillion stars. Unlike IC1101, which is an elliptical galaxy that stopped forming stars long ago, UGC 2885 is still actively forming new stars. How a spiral galaxy grew so large without being disrupted by mergers is something of a mystery. It likely grew through steady accretion of gas rather than through major galaxy collisions. Then there's the question of mass. The most massive galaxies aren't necessarily the largest in extent. Some galaxies pack enormous amounts of matter into relatively compact regions. Brightest cluster galaxies like IC1101 are among the most massive single structures, but even more massive are the galaxy clusters themselves. The Shapley supercluster, for instance, contains thousands of galaxies with a combined mass of roughly 10 quadrillion suns. It's not a single galaxy, but it's gravitationally bound and could be considered a single structure. For brightness, there are hyperluminous infrared galaxies that outshine the Milky Way by factors of thousands. These are typically galaxies undergoing intense star formation, or hosting extremely active galactic nuclei. They're not necessarily large in size, but they're pouring out energy at prodigious rates. Some quasars' active galactic nuclei in the early universe are so bright, they can be detected across billions of light-years, despite being relatively compact objects. The discovery of Alcyoneus teaches us several important lessons about the process of scientific discovery. First, sometimes the most extraordinary finds are hiding in data we have already collected. The limitation isn't always our instruments, but our ability to process and interpret the vast amounts of data those instruments produce. Second, expectations can blind us. If you're only looking for typical size radio galaxies, you might miss giants because they don't fit the pattern. Third, serendipity plays a role. The team that found Alcyoneus was conducting a systematic survey, but they were also open to being surprised by what they found. There's a broader lesson here about the nature of records and extremes. In any large population, whether it's galaxies, stars, planets, or even human achievements, there's a distribution. Most members cluster around average values with fewer examples at the extremes. But the extremes tell us about the limits of what's possible. They probe the boundaries of physical laws and environmental conditions. Finding the largest galaxy isn't just about claiming a record. It's about understanding what factors allow such extremes to exist. Consider what we've learned from Alcyoneus beyond just its size. We've learned that relatively modest central engines can create enormous structures given the right conditions. We've learned that environment matters as much as intrinsic properties. We've learned that low-density regions of space can host the largest single galaxy structures. These insights apply to understanding galaxy evolution more broadly, not just to explaining one record holder. The search for giant radio galaxies also has practical implications for cosmology. These objects, spanning millions of light years, can serve as probes of the large-scale structure of the universe. Their jets and lobes interact with the intergalactic medium, heating and stirring the gas. This feedback affects how gas cools and forms stars, regulating galaxy evolution on cosmic scales. Understanding the population of giant radio galaxies helps us understand these feedback processes. Moreover, the distribution of giant radio galaxies across cosmic time can tell us about the evolution of active galactic nuclei and the availability of gas to fuel black holes. If giant radio galaxies were more common in the past, that might indicate denser environments or more abundant gas. If they're becoming more common in recent times, that might reflect changes in galaxy merger rates or the decline of star formation, freeing up gas for black hole accretion. What about other types of extremes in the universe? The smallest galaxies, dwarf galaxies with just a few million stars, face their own challenges and reveal their own physics. The fastest spinning stars, rotating at hundreds of kilometers per second, push the limits of how fast an object can spin before being torn apart. The densest objects, neutron stars with matter compressed to nuclear densities, show us exotic physics that we can't reproduce in laboratories. Each extreme teaches us something about the range of possibilities in our universe. One of the most exciting aspects of astronomy is that we're constantly finding things that surprise us. Just when we think we understand the limits, how large galaxies can grow, how massive stars can be, how fast objects can rotate, nature presents us with something that pushes beyond those limits. The universe has been conducting experiments in extreme physics for 13.8 billion years, far longer and across far larger scales than we could ever achieve artificially. Our job as astronomers is to observe the results and try to understand what they mean. Do you ever wonder what other surprises are waiting to be discovered in data sets that already exist, or in the next generation of surveys that will see deeper into space and time than ever before? The universe has a way of humbling us with its diversity and creativity. Every answer we find generates new questions, and every frontier we cross reveals new horizons beyond. As we near the end of our journey through these cosmic giants, it's worth stepping back and reflecting on what we've learned, and what it means not just for astronomy, but for how we understand our place in the vast tapestry of existence. The story of Alcyoneus and IC1101 isn't just about measurements and physics. It's about perspective, wonder, and the human drive to understand the cosmos that surrounds us. We've traveled a long way together tonight, from that cold February evening in 2022, when astronomers first recognized Alcyoneus in their data through the physics of supermassive black holes, and relativistic jets across billions of light years and billions of years of cosmic time. We've met two extraordinary galaxies, Alcyoneus, the current record holder at 16 million light years across, and IC110, the stellar giant with 100 trillion suns. We've explored how they formed, why they grew so large, and what their existence tells us about the universe we inhabit. Now, as we prepare to let these cosmic giants fade into the peaceful darkness of contemplation, let's reflect on what this journey has revealed, not just about galaxies, but about the nature of discovery itself. The story of Alcyoneus is in many ways a story about expectations and surprises. Scientists expected that the largest galaxies would have the most massive black holes, the most powerful jets, the most extreme properties across the board. What they found instead was that an ordinary galaxy with an unremarkable black hole could create the largest structure ever discovered simply by being in the right place at the right time. The 16 million light-year span of Alcyoneus isn't the product of exceptional power. It's the product of exceptionally favorable circumstances. The low-density environment around the galaxy allowed its radio lobes to expand unimpeded for hundreds of millions of years, reaching sizes that would have been impossible in a denser setting. This discovery challenges one of our deep intuitions about how the universe works. We tend to think that extreme outcomes require extreme causes. The tallest mountains must have the most violent tectonic forces. The brightest stars must be the most massive. The fastest rivers must have the steepest slopes. But Alcyoneus shows us that context can matter as much as capability. A modest engine in the right environment can achieve what a powerful engine in a constrained environment cannot. There's a lesson here that extends beyond astronomy. Potential doesn't exist in isolation. It's always in relationship with circumstances, opportunities, and the resistance or lack thereof that the environment provides. IC110. One, by contrast, represents a different kind of extreme. Its 100 trillion stars, its supermassive black hole pushing the theoretical limits of how large such objects can grow, its golden glow from 7 billion-year-old stars, these speak to a galaxy that has lived long and consumed much. Sitting at the gravitational center of the Abell 2029 cluster, IC110, one has been the ultimate beneficiary of its location. Smaller galaxies have fallen toward it over billions of years, adding their stars to its growing collection. The intra-cluster light surrounding it, those homeless stars torn from their parent galaxies, testifies to a violent history of cosmic cannibalism played out over eons, where Alcyoneus achieved size through expansion into empty space. IC110. One achieved it through accumulation of matter. Both are impressive, but they took different paths to greatness. It's a reminder that there are multiple routes to any destination, multiple ways to achieve extraordinary outcomes. The universe is vast enough, old enough, and diverse enough to produce giants through many different mechanisms. What have we learned from our exploration of these cosmic titans? We've learned that size can be measured in multiple ways, and that different definitions of largest can crown different champions. We've learned that supermassive black holes can power jets that carve channels through space for millions of light years, depositing energy equivalent to billions of supernovae into enormous radio-emitting lobes. We've learned that the environment surrounding a galaxy, the density and pressure of the intergalactic medium, can determine whether those lobes grow to modest sizes or break all records. We've learned that galaxies evolve over billions of years through mergers slowly building mass and complexity. We've learned that the universe has a kind of life cycle from the small, irregular galaxies of the early universe to the massive quiescent ellipticals of today. We've learned that we live in a special era, the stelliferous era, when stars still shine and galaxies still sparkle with ongoing star formation before the long decline into darkness that awaits in the far future. But perhaps most importantly, we've learned that the universe still holds secrets, Alcyoneus was discovered just 2 years ago, aiding in data that had already been collected. How many other giants are waiting to be found? The astronomers who discovered Alcyoneus believe there are larger cousins lurking in existing surveys too diffuse or too unusual to have been flagged by current detection algorithms. The next generation of radio telescopes, the Square Kilometre Array in particular, will see deeper and farther than ever before, almost certainly revealing structures that dwarf even Alcyoneus. This ongoing process of discovery is what makes science so compelling. We never reach a final answer, a complete understanding. Each discovery opens new questions. Why did Alcyoneus grow so large with such a modest black hole? What determines whether a radio galaxy becomes a giant? How common are these objects in different epochs of cosmic history? What role do they play in heating the intergalactic medium and regulating galaxy evolution? The answers to these questions will require more observations, more sophisticated models, more careful analysis. The work continues. There's something deeply satisfying about this incompleteness. If we understood everything, if every question had been answered, the universe would be a less interesting place. The fact that mysteries remain, that surprises await, that our current understanding will certainly be refined and possibly revolutionized by future discoveries, this keeps astronomy vibrant and alive. Every generation of astronomers finds things the previous generation missed or misunderstood. Every new instrument reveals structures that were invisible before. The universe keeps teaching us that it's stranger and more wonderful than we imagined. Think about the journey humanity has taken to reach this point of understanding. For most of our existence as a species, we didn't know that galaxies existed beyond our own. The Milky Way was the universe, and those fuzzy patches of light in the night sky were mysterious nebulae of unknown nature. It took Edwin Hubble's observations in the 1920s to prove that Andromeda and other spiral nebulae were actually distant galaxies' island universes in their own right. That was less than 100 years ago, within the lifetime of some people still alive today. From that revelation, progress accelerated. We mapped the distribution of galaxies and discovered they weren't randomly scattered, but organized into clusters and superclusters. We discovered that the universe is expanding, carrying distant galaxies away from us. We detected radio waves from space and found that some galaxies emit powerfully at radio wavelengths, revealing the presence of jets and lobes. We sent telescopes into space to observe wavelengths that Earth's atmosphere blocks. We built interferometers that combine signals from multiple telescopes to achieve resolution impossible with single instruments. Each technological advance revealed new phenomena. The Hubble Space Telescope showed us galaxies as they appeared billions of years ago, allowing us to watch cosmic evolution unfold. X-ray telescopes revealed hot gas in galaxy clusters and energetic processes around black holes. Infrared telescopes peered through dust to see star formation in the distant galaxies. Radio telescopes like LOFAR mapped the radio sky with unprecedented sensitivity, revealing giants like Alcyoneus that previous surveys had missed. William Herschel, who first observed the C1101 in 1790, had no conception of what he was looking at. He saw a fuzzy patch of light and cataloged its position. He couldn't have imagined that it was a collection of 100 trillion stars, a galaxy 1,000 times more massive than the Milky Way, sitting over 1 billion light-years away. The technology to measure such distances, to resolve individual galaxies, to understand their nature, none of it existed in Herschel's time. He was seeing something extraordinary without knowing what it was. In a sense, we're always in Herschel's position. We're observing things we don't fully understand, cataloging structures whose true nature will only become clear to future astronomers with better instruments and deeper theories. The humility to recognize the limits of our current understanding, combined with the confidence to push those limits through careful observation and creative thinking. This is the essence of the scientific endeavor. What does all this cosmic grandeur mean for us, for our lives, on this small planet orbiting an ordinary star? It's easy to feel insignificant when confronted with galaxies spanning millions of light years, containing trillions of stars evolving over billions of years. We're tiny, fleeting, localized. Our entire civilization is a brief spark in cosmic time confined to one small world. And yet, we're the ones who figured this out. We're the ones who built the instruments collected, the data developed, the theories, and came to understand at least partially what these cosmic giants are and how they work. There's something remarkable about consciousness arising in the universe, and then turning its attention outward to study the universe itself. We are, in Carl Sagan's famous phrase, a way for the cosmos to know itself. The atoms in our bodies were forged in stars that exploded billions of years ago. We're made of stardust, literally. And now, assembled into this particular configuration, we call human beings. Those atoms are contemplating galaxies, measuring light years, calculating the masses of black holes, tracing the history of cosmic evolution. That's extraordinary. The perspective we gain from studying the cosmos can be both humbling and empowering. Humbling because it reveals how vast the universe is and how tiny our corner of it. Empowering because it shows what human curiosity and ingenuity can achieve. From this small planet using instruments we've built with our hands and minds, we've reached out across billions of light years to understand structures that dwarf anything in our everyday experience. We've looked back billions of years in time to see the universe as it was in earlier epochs. We've mapped the distribution of matter across cosmic scales. That's something to be proud of. As you drift towards sleep tonight, I invite you to carry with you the images we've explored. Picture Alcyoneus, that cosmic giant stretching 16 million light years, from end to end, its radio lobes glowing with the faint signature of particles accelerated to near light speed hundreds of millions of years ago. Picture I, Ceben 1101, with its 100 trillion stars, a golden empire of ancient suns, slowly orbiting the ultramassive black hole at its core. Picture the cosmic web, that grand structure of filaments and voids extending across the observable universe, with galaxies scattered along the filaments like cities along ancient trade routes. These structures exist, whether we observe them or not. Right now, as you listen to these words, Alcyoneus continues its journey through space, though we're seeing it as it was 3 billion years ago. The galaxy in its present state continues to exist somewhere out there beyond our light cone, evolving in ways we can't yet observe. IIC 1101 continues its slow accretion of neighboring galaxies, adding incrementally to its already staggering mass. New stars are being born in galaxies across the universe, while old stars are dying, returning their enriched material to the cosmic recycling bin to be used again in future generations. The universe doesn't care whether we understand it. It proceeds according to physical laws, indifferent to our observations and theories. And yet, understanding matters to us. It satisfies something deep in human nature, the curiosity that drove our ancestors to explore new lands, to chart the stars, to ask questions about where we came from and what the world is made of. That same curiosity drives modern astronomy, sending us in search of ever more distant galaxies, ever more extreme phenomena, ever deeper insights into the nature of reality. Have you ever stood under a truly dark sky far from city lights and felt that mixture of wonder and peace that comes from contemplating the stars? That feeling, that connection to something vast and ancient and beautiful, is available to anyone who takes the time to look up. You don't need a telescope or a physics degree. You just need clear skies, dark conditions, and a willingness to let your mind wander across the light years. The stars you see with your naked eye are all relatively nearby, within a few thousand light years, at most all part of our local stellar neighborhood within the Milky Way. But knowing that beyond those visible stars lie billions more organized into galaxies, and beyond those galaxies lie billions more organized into the cosmic web, that knowledge adds depth to the experience. You're not just seeing points of light. You're seeing into a universe of almost unimaginable scale and complexity, A universe that has been evolving for 13.8 billion years and will continue evolving for trillions more. The search for the universe's largest structures continues. Even as we speak, radio telescopes are scanning the skies, collecting photons that have traveled across billions of light years. Computers are processing that data, looking for patterns that might reveal new giants. Astronomers are developing new theories to explain what they observe, refining their understanding of how galaxies form and evolve. The Square Kilometre Array, when completed, will open new windows on the radio universe. The James Webb Space Telescope is already revealing galaxies in the early universe with unprecedented clarity. Future instruments we can barely imagine will extend our reach even farther. Each generation of astronomers stands on the shoulders of those who came before. Herschel cataloged fuzzy patches that later astronomers identified as galaxies. Hubble proved those galaxies were distant and measured their recession velocities, establishing that the universe is expanding. Radio astronomers discovered jets and lobes, revealing the violent activity of galactic cores. The LOFAR team found Alcyoneus pushing the size record to new extremes. Future astronomers will find structures that make Alcyoneus look small by comparison, or perhaps they will discover limits to how large structures can grow boundaries set by the physics of the universe itself. This is the beauty of science. It's a collective cumulative enterprise. No single person discovers everything. Each contributes a piece to the puzzle, and gradually over decades and centuries, the picture emerges. It's a collaborative effort, spanning generations, with each generation adding to what came before. The questions we ask today are built on answers found yesterday. The discoveries we make today will inform the questions asked tomorrow. Thank you for joining me on this journey through the cosmos, exploring these magnificent galactic giants and the universe they inhabit. I hope you found wonder in the scales we've contemplated, insight in the physics we've explored, and perhaps even a measure of peace in the cosmic perspective we've gained. The universe is vast, ancient, and filled with structures and phenomena that challenge our imagination and expand our understanding. As you drift off to sleep tonight, know that the cosmos continues its grand dance. Galaxies spinning through space, stars being born and dying, black holes accreting matter and launching jets, radio lobes expanding into the intergalactic void. And somewhere out there, perhaps in data already collected or in observations yet to be made, even larger, structures are waiting to be discovered, ready to surprise us once again, with the universe's capacity to exceed our expectations. Sleep well, and we'll meet again soon with more stories from the edge of human knowledge, more journeys into the depths of space and time. The universe has so many more wonders to share, and we've only just begun to explore them. Until next time, may your dreams be filled with starlight, and may your curiosity carry you to distant galaxies and beyond. Good night.